So now let's have a look at problem 13.1 and 13.2 together. So in both these problems we are given different matrices and we are asked to either use the singular value decomposition to calculate the rank or to simply get an understanding or intuition towards singular values and singular vectors and how that is related to the rank of the matrix. So let's name these matrices. Let's call this A1, let's call this A2, let's call this A3, let's call this A4, A5 and A6. So A1 is given by these numbers 2 4 6 1 2 3 1 3 4. Now one thing to notice here is that the first column is basically the second column multiplied by 2, and therefore if we take an arbitrary input x, ax could be written as, so 2 4 6 1 2 3 1 3 4 times x1 x2 x3 would give us x1 times 246 plus x2 times 123 plus x3 times 134. Now because 246 is just 2 times 123, we can write this as 2x1 plus x2 times 123 plus x3 times 1 3 and 4. So what we see is that for any input x, which is x1 x2 x3, the vector x, the output ax has to belong to the span of 1 2 3 and 1 3 4. So the output has to belong to a span of these two vectors. What this means is that there is at least one direction which is orthogonal to these two. Now because A maps R3 to R3, because it's a square matrix, it's mapping three-dimensional vectors to three-dimensional vectors, we have at least one direction in the output that cannot be reached by any input. Now let's try to write down the singular value decomposition. So what we know is that all these vectors v1, v2 and v3 are orthogonal to each other and therefore span R3. Similarly, these three vectors are orthogonal to each other and also span R3. But now we've just seen that A can have only outputs in a two-dimensional plane which is spanned by these two vectors. So we have to have at least one direction which cannot be reached by A, and therefore at least one singular value has to be 0. So at least one singular value, let's say sigma 3, should be 0. So now if no singular value is 0, so that means if sigma 1 is not 0, sigma 2 is not 0, sigma 3 is not 0. We can clearly have inputs in three different orthogonal directions. So AU1 would give us sigma 1 V1, AU2 would give us sigma 2 V2, and AU3 would give us sigma 3 V3, none of which are 0. So we would have outputs in all three orthogonal directions, which is contradicting what we saw earlier. So just to recall, we saw that the output has to belong to this two-dimensional subspace spanned by these two vectors. So now that is what we see. So we see that if A has linearly dependent columns, one of the singular value has to be 0. And this is what we indeed see if we now go to MATLAB and uh, use the SVD command to do a singular value decomposition of the matrix A. Additionally, once we do the singular value decomposition, we also get the direction V3 corresponding to the 0 eigenvalue, corresponding to the 0 singular value, which tells us that V3 is the direction which cannot be reached by any input to A. So now let's have a look at A2, which is given as this here, and let's try to do this just by inspection. So let's first so A2, see that A2 is mapping R2 to R3 because A2 has 3 rows and 2 columns. The input to A2 are two-dimensional vectors and the outputs are three-dimensional vectors. So let's choose the two canonical input vectors and have a look at the output. So AU1 when, so this is A2. A2U1 when U1 is 1 0 is nothing but 2 0 0, which can be written as 2 times 1 0 0. U2 gives us 0 minus 3 0, which can be written as 3 times 0 minus 1 0. Note that this vector and this vector are also orthogonal to each other. So what we have is 8 times 1 0 0 1 is equal to 0 0 0 minus 1 0 times 2 0 0 3. So if you notice, this is not quite the single value decomposition because this can pass as a U because this is orthogonal, but we need to do some work on the right hand side. Now because we need a V which is orthogonal, we can observe that the right hand side can be written as 0 0 0 minus 1 0. Now I augment an additional third vector which is orthogonal to the first two and accordingly add some zeros to keep the equality. So now we have a V which is orthogonal and a sigma which is the same size as that of A2. Note that this is A2. So that's our singular value decomposition. So what we see is that for diagonal matrices such as A2, the single values are nothing but the absolute values of the diagonal entries. So because 2 is positive, it stays as it is, but we have a negative 3 which becomes plus 3 as the singular value. So now let's look at A3, which is just a column vector here. So A3 is R3 by 1, and it can be seen as a map from scalars to three-dimensional vectors. So what we have is for arbitrary inputs u, where u is a scalar now, the output is just u times minus 1 to 2. So output belongs to the span of a single vector. So now let's try to write down the singular value decomposition for E3. We'd have a single u, u1, and three vectors v1, v2, v3. So we can pick u1 as 1 because that's just a scalar and we need to normalize it. We can normalize, we have to pick v1 along the output direction, but we need to normalize it to get this. v2 and v3 are arbitrary vectors orthogonal to v1 and normalized. So for example, we could use Gram-Schmidt orthogonalization to compute them. Now what remains is to compute sigma 1. So for this, let's write down the first equation, which is A3U1 is sigma 1 V1, which is nothing but minus 1 to 2 times 1 is equal to sigma 1 times V1. V1 is nothing but 1/3 times minus 1 to 2. This means that sigma 1 has to be equal to 3, which is nothing but the norm, the Euclidean norm of A3. So there is an alternative. So we did this just to get a better understanding of the singular value decomposition. There is, however, a very quicker way that we could have used to compute the singular value for this one. So what we have is that singular values of A are square roots of the eigenvalues of A transpose A. Now if A is a column vector, so let's call this A3 because that's our example here. If A3 is a column vector, A3 transposed A3 is nothing but the norm of A3 squared. So if A3 is a column vector, so which is nothing but just a scalar, and the eigenvalue of a scalar is the scalar itself. So we have that the Singular value of A is nothing but the norm of A3. So let's now have a look at A4, A5, A6, all of which are 2 by 2, so square matrices, and we want to see how the singular value decomposition tells us something about the rank of the matrix. So let's first recall that the singular value decomposition of A leads to AU times V sigma, where U and V are orthogonal matrices and sigma is a diagonal matrix because the same size of A, and because A here is a square, sigma is also square and 2 by 2. Now this just means that A is V sigma U transpose, which now I write down as V1 V2 for 2 by 2 matrices, sigma 2 times U1 transposed and U2 transposed. Now you can work this out, but this can be written as V1, so sigma 1 times V1 U1 transposed plus sigma 2 times V2 U2 transposed. So this is obviously for A 2 by 2. Now let's have a look at A4 and A5. So A4 is epsilon 1 to epsilon 2. Notice that the second column is 2 times the first column, so we can clearly write this as epsilon 1 times 1 and 2. So let's call this V tilde and let's call this W tilde transposed. So we could define V as V tilde divided by norm of V and W as W tilde divided by norm of W tilde. So basically just normalize both these matrices and write down A4 as V times W transposed multiplied by norm of V times V tilde times norm of W tilde, and we can call this sigma, and we would get sigma times V times W transposed, or A4 equal to sigma times V times W transpose. Now we could add a vector orthogonal to V and a vector orthogonal to W and write this as 0 times V perp and W perp transpose, and so get the singular value decomposition as So we see that A4 is uh, uh, a one rank matrix, and that can be seen by doing the singular value decomposition. So similarly, A5 is given as this here, which can be written as 10 times epsilon 1. So repeating things that we did for A4, we can write this as V1 V2 sigma 1 0 W1 transposed W2 transposed, where sigma 1 is nothing but the norm of the first vector, which is just 1, times the norm of the second one, which is this one here. Now let's have a look at A6 here. We have this form for large values of epsilon. For example, if epsilon is 1, we have A6 as 1 1 and 1 2, which is full rank because we have independent columns here. So the key here is to observe that for small values of epsilon as compared to 1, A6 is almost equal to epsilon 1 and epsilon 1, which is not full rank. So what we know is that as epsilon goes to 0, A6 loses rank by 1.